Okay, we are live on YouTube. So welcome to the Silicon Valley chapter of IEEE Computer Society event. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE with over 3,500 subscribers in our mailing list and a strong following of over 12,300 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise, and thanks to the virtual mode of the events that the pandemic pushed us into, we are able to avail of expertise from all over the world. Like today, we have a distinguished visitor, Dr. Francisco Flamini. He graduated cum laude, obtaining a master's degree in 2003 and a research doctorate Ph.D. in 2006, both in computer engineering from the University of Naples, Federico II, Italy. He worked for 15 years in private and public companies, including Ansaldo STS, which is now Hitachi Rail, and IPZS, Italian Statement and Polygraphic Institute, on large international projects addressing intelligent transportation, critical infrastructure protection, and cybersecurity. He was a technical leader and also a unit head. Since 2020, he has been a full professor of computer science with a focus on cyber physical systems at Mälardalen University in Sweden. And he's also the technical manager of the Rail European Union funded research project about artificial intelligence for smart railways. He is a professor of trustworthy autonomous systems at the University of Applied Sciences and Arts of Southern Switzerland, where he is affiliated with Dalle Mole Institute of Artificial Intelligence. Previously, he has been a senior lecturer and the chair of the Cyber Physical Systems Environment at Linnaeus University in Sweden. He is a senior member of IEEE and a member at large of the IEEE SMC Board of Governors. He co-authored or authored 150 plus technical publications, and he has served as a chair, invited speaker, steering program committee member, and editor for several international conferences and journals. So today he's going to talk about a vision for intelligent train control, which is eagerly awaited by many of you. I've been getting inquiries about this talk. The synopsis of the talk is something like this. The progressive adoption of artificial intelligence and advanced communication technologies within railway control and automation gave rise to a huge potential in terms of optimization, learning, and adaptation due to the so-called self-fix capabilities. However, it has also raised several dependability concerns due to the lack of measurable that is needed for certification purposes. So in this talk, a vision will be provided about future train control that builds upon existing automatic train operation, protection, and supervision paradigms. The basic concepts for autonomous driving and digital railways will be provided, and a feasibility will be addressed in terms of challenges and opportunities, including explainability, autonomic computing, and digital twins. So all exciting technologies driving today's economy. Due to the clear architectural distinction, traditional train protection can act as a safety envelope for intelligent operation to optimize energy, comfort, and capacity, while intelligent protection based on signal recognition and obstacle detection can improve safety through advanced driving assistance. So let us hear more about these ideas and thoughts and in the vision for a intelligent train control. So over to you, Francisco.
Thank you very much for this nice introduction. So I don't need to introduce myself again. I will just say that I am affiliated with both Computer Society and the SMC, Systems Man and Cybernetics Society, for which I am a member of the Board of Governors. And I'm also a IEEE senior member. I will present today one of my talks as a distinguished visitor of the IEEE Computer Society, which is focused on intelligent train control. As you have understood from my introduction, most of my experience has been in industry, and I've been more than 13 years employed in a company developing railway control systems. So this is why my research in academy has been mostly a continuation of what I learned and I did during my industry experience. But I like to start from a broad view of what is a smart city today. So as you can see in this slide, basically a smart city includes all modern technologies that are based on intelligent sensors, collecting a large amount of data, and all the technologies that are needed to transmit this data, store this data, analyze this data. And there has been a huge interest in the last years in big data analytics, artificial intelligence, and machine learning. So among all the sectors in which you could use these technologies and which these technologies are used, including smart manufacturing, so industry 4.0, smart health, you have smart transportation that includes all modes of transportation. But in particular, there is a mode of transportation among the most common ones, which is railways. So we are talking about smart railways, which is greener than the others. So the carbon footprint of railways is limited, much limited compared to the other modes of transportation, such as air transportation or cars or taxi, other kinds of land transportation. So this is why there has been a huge interest and huge investments all around the world, but I'm specifically focused in Europe, from the European community, in improving the technologies that are used for railways and investing in artificial intelligence for railways. This is why there has been this call, and we applied to this call. Not only me, I've been the technical manager in this project, but together with some other partners in Europe, so in Sweden, UK, Italy, and Netherlands, we have started this project about roadmaps for AI integration in the rail sector that was funded by the Shift to Rail joint undertaking within Horizon 2020, which is now, it's changed its name to Europe's Rail. And if you want to know more about this project, I've put in this slide the link to the website, and there are also a couple of social channels on LinkedIn and Twitter, in which you can find all the latest news about the project, which is going to finish soon. So we'll provide a summary of the results of the project in this talk, with a specific focus on one of the areas that has been addressed in the project, because overall the project has a broad scope addressing AI in railways for rail safety and automation, predictive maintenance and defect detection, traffic planning and management. So what we did was to provide a picture of the state of the art of artificial intelligence in railways, and in the end we defined the future roadmaps for the adoption of these technologies. But of all the aspects that have been addressed in the project in this talk, I will address specifically rail safety and automation, which is the part that is under WP2 work package number 2. But let's start with the basics, because I guess that not all of you are experts of railways, of modern railways. So we'll just provide basic definitions of what is automatic train operation, which is identified with the acronym ATO. That technology is used to automatically drive the train and stop at stations when needed. Then you have another layer, technological layer, which is the automatic train protection subsystem, ATP, which is used to automatically stop the train or applying the brakes when needed, when the speed is over a certain threshold. Then the automatic train control is a combination of ATP and ATO. So you have potentially full control of the train even without the train driver. So this is what happens in driverless trains. And then there is the supervision system, ATS, that manages train schedule and coordinated routes along the rail tracks. Now, how does it work? Well, there are a lot of different implementations of this system, so we'll just provide one which is representative of modern railways. This is based on the European Railway Traffic Management System, European Train Control System, which is the modern standard that has been used for European railways, not only in Europe, but it has been exported in many other countries outside Europe. And this is one possible implementation of ERTMS ETCS, which is based on moving block signaling, which is the most advanced signaling system within the standard. As you can see, you have two trains, and you need to make them move without avoiding collisions between these two trains. So you need to ensure the safe distance between the trains. So how do you do that? Trains, they send their positions to this entity, which is known as the radio block center, which is responsible for train separation. And in this information is the so-called position report. The train transmits to the radio block center their exact position together with other information. And knowing the position of all the trains, the radio block center can send to the trains the so-called movement authority, which is this distance that all the trains can run safely, so without risking any accident or impact with other trains. The onboard system, the one on board the train, uses this information to build a braking curve. So the movement authority allows the train to compute this point, the end of authority, or protected point, which is the end of the movement authority. And then the maximum speed that the train can travel is represented by this braking curve, which is also known by dynamic speed profile. So this is how it works. The onboard system computes and applies this braking curve. So the automatic train protection is responsible that the train never goes over this braking curve. So this means that the train can travel safely over the track. Okay, so this is the basic way modern railway signaling works. So everything is computer-based and messages are transmitted over wireless networks. But then you have another kind of representation and classification that is based on the grades of automation. In grade of automation 0, the train operations are manually supervised by the driver. So this is the traditional way railways operate. And then you can go up to level 4, so grade of automation 4, in which you have unattended train operation, in which you don't need any driver or staff on board the train. Now, from the previous definitions, we never mentioned AI. So even full automation, driverless trains that have been around for more than 30 years, they don't have AI on board. So this full automation is implemented by full segregation of the rail track. So you have platform screen doors, for instance, so you don't have to detect people or other obstacles on the track, because you have a physical separation of the track that ensures the safety. But we want to move a step further and think about the possibility of implementing driverless trains in open environments. So when you don't have this segregation in normal railways, commuter railways, this is the situation. So in order to ensure safety, you need to have some mechanisms on board or on track that detect, for instance, obstacles on the track. But let's start from the middle part of this figure in this slide and this diagram, in which we assume that we want to move from automatic train operation, which is what is already available today, to intelligent train operation. What does it mean? That we want to optimize train operation, for instance, to reduce the energy consumption, to optimize the capacity of the track, or to improve the comfort of passengers. This we can do provided that we have the automatic train protection that acts as a safety envelope. So the movement of the train is, even if it is intelligent, so there is some advanced mechanisms based on machine learning, it is protected by this envelope. So you have the braking curve, so everything can happen if it is within the braking curve, but if not, if the speed, for instance, is higher than what is allowed by the braking curve, then the automatic train protection will apply safe braking. So this works quite well and does not represent a threat for the safety of passengers. So I put here this indication can be certified up to C4, Safety Integrity Level 4, which is the, according to the SCV standard, this is the maximum level of security which is needed to implement train control systems. And you have in modern railways this certification against this C4 level according to the SCV standard. But what is the challenge? If you want to add intelligent train protection, so if you want to make obstacle detection, because you want to help the train driver as a driving assistance mechanism, as you have in self-driving cars, or you want to make the train full autonomous, then you need to detect obstacles and also recognize signals if you have signals on the track. And this is challenging. Why? Because you need artificial vision, and artificial vision is based on machine learning and specifically on deep learning, convolutional neural networks, and this is considered as a black box. So you have this opacity problem. So if you want to certify these technologies to be safe according to the existing safety standard, this represents a big challenge, which has no solution nowadays. Even if you just want to use these technologies to aid the movement on train in specific scenarios, for instance, when you don't have full supervision by the automatic train protection because you have a shunting scenario, you have a failure that makes the train switch to the on-site operating mode or staff responsible operating modes, still these technologies need to be, to some extent, verified and certified according to some safety integrity level, which even if it is not SIL4, should be SIL3 or SIL2, depending on the scenarios and the maximum speed, and if you have the driver on board or not. Okay, so this is the full picture, but that we will analyze step by step. So first of all, together with the Rails project, we started this series of workshops that are known as AI for Rails, Artificial Intelligence for Railways. It started in 2020, and we had the first submissions to this workshop series already addressing the problem of using AI for obstacle detection in railways. Then in the following years, we had further studies, and most of these studies they came from funded European projects such as SMART and Tauro. So, but in this Rails project, we had a broader view, as I said. So we wanted to understand not only obstacle detection, but the full picture of intelligent railways. So we dared to define some grades of intelligence, which, as I said, is not the same of grade of automation, because you can have full automation with no intelligence. In this case, we wanted to highlight the role of artificial intelligence, and I will come to the maximum level, which is the grade of intelligence 4. At this level, you have all the possibilities that are enabled by AI and all the technologies together with AI. So, for instance, the Internet of Things. In this case, you have a system which has advanced learning and adaptation capabilities. So it learns from the environment, it adapts to the environment, and uses this knowledge to, for instance, to predict accident based on the past history of derailment. For instance, can use that data to anticipate, or knowing something that has happened in the other part of the world on similar systems, it can learn and adapt and improve and even anticipate accidents. So this is the maximum thing that we can get with AI. Is the most visionary implementation of artificial intelligence in railways. What you need to do this, you need a lot of things. For instance, one thing that is understanding of what you need is the use of the MAPK loop, and this paradigm is associated with autonomic computing and is used a lot by the community of researchers doing their research in self-adaptive systems. And we did this parallelism with the self-driving car reference technologies. On the bottom, you see that you have all the railway infrastructure equipment, trains, track, and stations. Then you start with the monitor phase, in which you have data acquisition. Then in the analyze phase, you have the real perception. Then you have planning, in which you do planning and control. And then finally, in the execute phase, you do actuation. And all these phases are based on the shared knowledge. So the MAPK stands for monitor, analyze, plan, and execute over a shared knowledge. So this is an important paradigm that allows to divide the big problem into sub-problems, so they are easier to address. But let's come back to the levels of intelligence. Of course, levels of intelligence can be if a system associated to the fact that the system is less or more intelligent, but it can also associate it to the level to the levels in terms of computing levels. And we know that nowadays we divide the computing levels into at least three levels, which is edge intelligence, in which you make this computation on edge devices. Then you have fog intelligence, which is an intermediate layer, in which you have local area networks or campus or metropolitan area networks. And then you have cloud intelligence, in which you have a data center somewhere in the world, in a remote area of the world. What are the pros and cons? Of course, at edge intelligence, you have less computing power, less storage, because you have less powerful devices, but they are close to the real physical infrastructure. So you will have reduced latency. You have more privacy, more security, because your data will not circulate over the internet and to reach the remote data centers. So you can provide more real-time response, but you have limitations in the knowledge that you have. Instead, the more you move up to the cloud intelligence, you have more power, more computing power, more storage, and more intelligence that is collected by all the devices possibly installed in large geographical regions or all over the world. One more thing that can enable these higher levels of intelligence is we said that we can use this autonomic management based on the MAPE-K loop, and we can use another paradigm, which is the paradigm of digital twins. So basically, this MAPE-K loop is somehow embedded in a digital twin, which is a representation of the real system. So you have you might have a very detailed model of the physical or the real system, not necessarily only hardware, but you can have a replica of both the hardware and the software of the real system. And this can be used to, for instance, simulate, make what-if analysis, apply predictive analytics to anticipate what can happen if I take this decision. So this is the paradigm, and you can have at the edge level with some limitations, as I said, but then when you move up to the cloud intelligence, you have basically no limitations. So you can have a super brain that can connect it to the trains, to the stations, can allow any kind of predictive analysis. Another important point here is how you ensure trustworthy artificial intelligence. When we talk about obstacle detection, signal recognition, when AI is used to perform critical tasks, then you have to ensure that AI is trustworthy. And this concept has been formalized recently. One formalization has been provided again by the European Union with this high-level expert group of professors and experts of AI who define trustworthy AI as an intersection between these three areas, which is the legal aspects, the ethical aspects, and the robustness aspects. So this is the more technical aspects related to safety, reliability, dependability, resilience. I mean, technical aspects, this robustness of machine learning is not enough. You also need to consider the legal aspects and the ethical aspects. So on the right side of this slide, you have representation using UML class diagram of trustworthy AI, a possible representation. Of course, you can have many different representations of what I have just said, which in the robustness, you have the traditional dependability attributes. In the lawful part, you have aspects such as accountability, privacy, and explainability that are important to certify your system. And then in the ethical aspects, you have fairness, respect, and transparency. But we will come back to some of these attributes later in this presentation. And we start with the explainable artificial intelligence, which is very, very important. Because, as I said, the most powerful techniques for AI that you have nowadays are not transparent. So they act as a black box. You have this problem of opacity. So they are very powerful. They can help take important decisions, but then the user, when he or she gets the decision recommendation, is not able to reply to these questions such as, why did you do that? Why not something else? When do you succeed? When do you fail? So basically, the user cannot trust the system. Instead, when you have explainable AI with an explainable model and an explanation interface that provides some interpretation of why the system has taken that decision, then there is a full understanding and knowledge. And in this scenario, you can get safety certification. Otherwise, I would say that it's impossible to have a safety certification if you cannot demonstrate and provide evidence that your system is safe. Then you have other issues. which is, for instance, this new class of threats against artificial intelligence, which are known as adversarial attacks. So people who want to create an accident, they can, knowing how the artificial vision works, can, for instance, change the shape of a stop signal and make the system think that it's another signal. So this, in these slides, you have the example of self-driving cars, but it will be the same with driverless trains. If you want to make robust signal recognition, you need to take into account these new categories of threats that didn't exist before the introduction of artificial intelligence. So in railways, you can have, as I said, many applications of artificial intelligence, and even within the use of AI for safe autonomous driving and for cooperative driving, there are a lot of possibility. One that I will not address in this talk is, for instance, this virtual coupling, which is a transfer into the railways of the concept of platooning that is has been researched for decades in automotive systems, and in the last years has been transferred to railways. So there are a lot of possible applications, but we will pick one possible application as an example in this talk, which is the detection of objects at level crossing, which is one of the applications that are really important. And if you talk with the railway companies, they know that accidents at the level crossing are unfortunately quite common. And the attempt to detect, for instance, vehicles at level crossings on the track using artificial vision is not a new thing, because it started more than 10 years ago, and you can use cameras and other sensors to do that. So it can be a reference application to understand whether we can do this safely or not. So let's start with this example. In this slide, you have another representation of a similar scenario. So you want to detect automatically the presence of a car on a track, and this is very important, for instance, in mixed intersection between car traffic and tramways, which is another possible scenario. And you want to use several technologies of sensors. Actually, you must use several technologies. Why? Because one of the keys to achieve safety is the use of redundancy and diversity. So you need more sensors with more technologies. And in this case, you have many options for the technologies that can be used for vehicle detection, because you have, for instance, active infrared, microwave radars, passive infrared, ultrasonic detectors, video image processing, which is basically artificial vision, acoustic sensors. So when you put these sensors together, you can imagine, it's quite intuitive, that you can have more power, and this power you can use to make your system safer. So coming back to the application of the MAPK loop, everything can be represented into this paradigm of monitor, analyze, plan, and execute. But the important thing in this case that we did in this research of the paper that I have mentioned in the previous slide is that we used this formalism of dynamic Bayesian network, which is a probabilistic modeling formalism that supports explainable AI, because differently from neural networks, in this case you have a precise representation of the model, which is transparent. So you have nodes and arcs and conditional probability tables, and these can represent the knowledge base that you want to use to sense what's happening in the real world, and then understand if you can trust the system when it takes a decision whether a vehicle is present or not at level crossing or intersections. How can you use this again within these paradigms as a set of digital twins? So within the digital twins, you have this MAPE-K loop. And then what you do is to start build a digital twin, because of course, if you don't have the digital twin and the reference model at the right level of abstraction, you cannot use this approach. Then you instantiate the digital twin at the same time with the initial configuration, and you evaluate the model continuously at runtime to understand what is the level of dependability of the system. The level of dependability of the system depends on, for instance, in the vehicle detection case study on whether all the sensors are working properly. If there are some conditions that affect the trustworthiness of some of the sensors, in that case, you have to exclude the sensors or reduce the reputation of those sensors. So when you have, for instance, a voting, you have a weighted voting based on the reputation. So the check that you do is that the dependability target can be achieved. So you can consider the system safe. If yes, then you can execute the system plan and the current configuration and update the digital twin with the field data. So if there is no fault or anomaly, you continue working this way. Otherwise, if there is a fault, you need to make a reconfiguration of the sensors. If there is an acceptable option, so still the system can be considered safe according to the safety integrity level quantitative requirements about the hazardous failure probability, you can apply this new configuration and then start again. Otherwise, if you don't have any acceptable options, the system cannot be made safe again according to the requirements of reference standard and required safety integrity level. Then you need to shut down or switch over to fallback procedure or other kind of redundancy. If you have a manual operating mode, if you have a possibility to control the system manually, then you will switch to manual mode. Otherwise, you need to stop the system and activate a fallback according to fail-safe mechanisms. So the same thing of this flowchart you can have with this is another view. It's the state chart in which you have a situation in which you have no faults and anomalies. Then you have minor faults of anomaly, multiple faults or anomalies. When you have a critical faults, then you need to shut down or switch over to manual operation. So this is how the system works according to these behavioral diagrams. So I don't go into the details of the results of the elaboration of the dynamic Bayesian network models, but in the end, you get results like this one that I've represented in this slide, in which you have a different sensor configuration. So here you have the acronyms of the different sensors that are used in the initial configuration, in which you have 4 out of 5 weighted voting, and you have this probability of hazardous failures, this number, which corresponds to a SIL2, safety integrity level 2, which is an intermediate one. And then changing the configuration, you can make it a little bit higher. For instance, with 4 out of 4, it's safer, but will be less available. Otherwise, there are other configurations which you have a probability of hazardous failure, which is a little bit higher. So this means that you will have a safety integrity level 1. We are only considering for the safety integrity levels the quantitative evaluation of the hazard rate. Then, of course, there are a lot of other activities in the verification and validation of the systems, such as, for instance, testing, code analysis, static analysis, model checking, and so on that are done at design time to ensure the fulfillment of these safety integrity levels. But we are just considering this reconfiguration at runtime and these new levels of hazardous failure rate. Regarding the still at runtime, but not quantitative analysis, but qualitative analysis, there is the possibility that you integrate in these digital twins and in this MAPE-K loop, not only the evaluation of the probabilistic evaluation of the hazard rate, but you can also use conformance checking, which is a technique that has been derived by the research area of process mining. So what you do basically is you have a reference specification of how the system should work. So this is either given by the system specification requirements, so you build this reference behavioral model, or you build from the system itself when you are sure that the system is operating in its nominal and correct way of behaving. Either way you build the system, this reference model, what you do is that you compare what is happening in the real system, collecting the event log and analyzing the event log, and you make a comparison with this reference model. So if the behavior is as expected, then you have the conformance checking is successful. If you detect some anomalies, then what you can do is to stop the system, which is the easiest way to do, or you apply other countermeasures to solve the anomaly. So this is a sort of complementary approach compared to the probabilistic evaluation, because in this case you make this conformance checking at runtime based on behavioral model of the system and how the system behaves. One more thing, so we are towards the end of this talk, how you implement digital twinning in practice. Well, this is another challenge because it's not an easy task. I mentioned how you build the model, but in addition to the model, you also need a software architecture to collect this data from sensors and elaborate this data, store this data. And what you want to do is to divide this big problem into sub-problems, so into layers and into modules, and each module is responsible for one piece of the full elaboration. So in this reference architecture that you see in this slide, you have an example of distinction between the managed subsystem, which is the real system. It's the train, is the railway, is the station, all the infrastructure, and then managing subsystem according to the autonomic computing paradigm is the one implementing the MAPE-K. So you have here these letters. MAPE is M stands for monitor, A for analyze, P for plan, and E for execute. And K is the shared knowledge. So we have these modules in the digital twin that are supposed to implement the MAPE-K loop, but this is done through a specific software architecture divided into layers, and in each layer you have different modules. One more thing is the usage of digital twins in the loop for mixed reality testing of machine learning systems. This is one other thing that is very important. It's not runtime analytics. It's something that you can do at design time, and it is how self-driving cars are tested in this combination of virtual environments and real environments. And you can have any combination of of real environments and virtual environments. For instance, in the case of railways, you can have a situation in which you have real train in the real environment. Then on the opposite, you have virtual train in the virtual environment, so everything is basically simulated. But you can have intermediate options in which you have virtual train running in the real environment and a real train running in the virtual environment. This is very important because it can speed up testing of these systems based on machine learning. And you can build safe scenarios that are close to the reality. And in the center, you have this mixed reality scenario in which you have the real infrastructure, so the real track. You can have the real train, but you can have a virtual obstacle, which is virtually put on the track to test the artificial vision, the obstacle detection safely and quickly, because you don't have to put real obstacles there. So this is one of the paradigms that can support the testing of machine learning systems in the railway context, together with all the other approaches that I have shown in the previous slides of this presentation. So we can summarize the key technical recommendations that are a result of some of the results of this project that I mentioned at the beginning of my talk. So one key recommendation is to work on common dataset generation and sharing. This dataset issue is very important because all these technologies are data-driven, and so they need training and testing. So there are some techniques such as deep transfer learning that can be used to support domain adaptation. So to solve or to partially solve the problem of missing dataset or difficulties in getting the datasets. Then what I have extensively shown in this talk is the use of digital twins. Together with AI, you can get the so-called cognitive digital twins, autonomic computing and self-adaptation, the MK loop, at distributed levels of intelligence, edge for cloud. And this allows to really achieve endless possibilities in predictive analytics for your system. One possibility is to reach proactive safety, and this is very interesting, and there is a lot of interest from some railway undertakings in Europe, but I'm sure that this is the same in the rest of the world, in which they want to use big amounts of data about the railway accidents to prevent future accidents in the same conditions. Then I have talked about mixed reality simulators and the importance of these simulators. It has been demonstrated, or it is being demonstrated mainly in automotive applications, self-driving cars, autonomous cars, but it is the same when you consider these technologies transferred to railways. And then you have a quite broad research area, which is the one of trustworthy artificial intelligence, which is really cross-discipline. We have mainly focused on the technical parts or on robustness, but there are a lot of different and equally important implications on ethical and legal aspects. And this is a key paradigm to enable autonomous train operation. Okay, that's all. Thank you very much for your kind attention. I would be glad to answer any questions.
Thank you, Francisco. That was really very insightful and interesting. So we have a few questions on the Zoom chat window. I'll go in the reverse order. Srini is asking, do we have any existing or upcoming IEEE standards to guide and govern this space of ITC?
Yeah, this is a very good question, because IEEE is very actively contributing to guidelines and standards for autonomous systems, for trustworthy artificial intelligence. So there is not only one initiative, but there are several initiatives within IEEE. Of course, not only within IEEE, because other standardization bodies are also actively working on the standardization for ethical AI, safe AI, and all these important aspects that I have mentioned in my talk. But for sure, IEEE has different working groups and standardization initiatives that are ongoing, but still have draft standards and sometimes even more stable standards that you can use to guide the design of these classes of systems.
Yeah, but is there any specific standard for just for the railways with IEEE?
Not to my knowledge. It's more broad. It's broader for autonomous systems more in general. So of course you can apply to autonomous railways as a specific class of autonomous systems. But to my knowledge, there is nothing that is specifically addressing railways.
Okay. And a question from Amit. In your last slide, what is not clear is how much progress has already been made and what the problems yet to be solved are.
Well, yes, this is about the state of the art, and I didn't address the full picture of the state of the art. I just want to mention that there are several ongoing projects at European level. So I could mention many projects worldwide, probably together with the European ones, but I'm more knowledgeable about what is happening in Europe. So you have these smart projects and these Tauro projects that are specifically addressing autonomous driving. So the project that I've been the technical manager of is this one, Rails, that it's broader, that includes all aspects of AI within railways, including predictive maintenance, smart maintenance, as I said in the beginning of this talk. While there are some other projects that started with building the state of the art, for instance, on obstacle detection in railways. And I can send you, if you drop me an email to my address, which is francesco.flamini@ieee.org. I can send you the specific state of the art that have been made in those projects on aspects such as obstacle detection in railways. So the problem has not been solved. Long story short is that we are still working on that. I mean, the research community and the industry is still working on that. We don't have an railway obstacle detection solution that can be installed on the trains and can be certified SIL 4. That is the situation nowadays, but there are a lot of advancements, and I see that there are news and papers that are being developed each month, and I see a lot of progress. So I trust that some results can be achieved in the next few years under some conditions, because as in other classes of autonomous vehicles, when you have AI technologies, it's difficult to say, okay, it will be safe in all conditions. But if you put some constraints and limit somehow the degrees of freedom, then in those cases you can use those technologies at least as driving assistance features.
So another question on the chat window is there a public data set of railway images and videos that can be used to address unsolved problems in this space?
Yes, this is another very good question, because it has been one of the recommendations from this project was to build such a data set. I mean, there are some data sets, so I cannot say that there is no data set. So we within the project, we also wrote one technical paper which was a survey of the existing data sets that can be used for artificial intelligence in railways for training and testing. And we found some, not many, but some are available, but they have some limitations and they cannot be used to as a reference benchmark. So what we want to achieve actually, what is very useful in our opinion, is to have a common repository on a specific website that all companies or research groups that are interested in these aspects can use those data sets to benchmark their technologies over a common baseline. So this is one recommendation from the project. So we believe that it will be really useful, but so far this is not something that is already available.
Okay, so you talked a little bit about federated learning, right? I mean, the edge fog cloud. So I was just curious, how do you address bias aspects in the local data set? And also, if you can give some insights into the kind of data that is being collected, is most of the data from the sensors, or is there any additional data that you use?
Well, in this project, as I said, this has provided a broader view, and there are other projects within this Europe's Rail Joint Undertaking. There are some projects that are specific to smart maintenance in railways. So they have studied more in depth how you can use the data to make better predictive maintenance. So we didn't address these aspects of reducing the bias in data and things like that specifically for some specific problems, but these have been identified as key issues and challenges to address, to tackle, and to overcome. So it's of course the quality of data is really crucial, and in the assumptions that we made in these pilot cases that we addressed in the project. One for instance was the smart maintenance at the level crossings, by understanding whether the warning bells or the movement of the barrier were okay, or there was any fault. We used some public available data sets, for instance YouTube videos with images of level crossings with the movement of the barriers and sound coming from the warning bells ringing, and even the light signals. So these have been used as sources to show the high-level paradigm of deep transfer learning. So how you can transfer this to your scenario, even if you don't have specific data set from a specific level crossing. So this is something that we did, but it's just part of the problem. It's solving this does not solve the whole problem. So the roadmaps that we have depicted, and we are still working on that because the project is almost finished, but not yet finished. It will formally finish the end of this month. Then we have some other months to finalize the deliverables. Then the final step is to define the roadmaps. Roadmap means that we haven't solved the problem. Of course, this is a relatively small project, so we could not solve all the problems, but we defined these recommendations and roadmaps for the future. So which are the problems that need to be addressed, and which are the possible solutions with an estimate of the degree of maturity of different technologies. So recommendations to invest in this and this, considering what we did in the project, but also the surveys that we asked to the railway experts, because this is another activity that we did in the project that I didn't mention in this talk, that we involved the community of experts and asked them what was their perception of the maturity of this technology in the form of technology readiness level. So you know that there are this estimation of maturity of technologies that are from TRL1, which is the lowest, to TRL9, which is the highest. TRL9 means technology that is ready to be industrialized and commercialized. So most of these technologies were at an intermediate level. So you have some proof of concept, some lab experimentation, but you are not very close to the possibility of selling these technologies to real customers.
Okay, the other question on the chat window is, you mentioned the benefits of AI railways in improving safety, obstacle detection, and so on and so forth. But are there significant service improvements like shorter headway, better on-time performance that can be made over standard moving block signaling as found in ETCS?
Well, one of the, still it's not something that I have addressed in this talk, but I can tell you that one of the areas that has been investigated in this Rails project that I mentioned is virtual coupling. Virtual coupling is the paradigm that has been introduced in railways that transfers platooning. So platooning in automotive is when you have multiple vehicles that are connected, for instance, trucks or even cars, so that they look like a train because all the vehicles are very close to each other and they move together in this cooperative driving. And this can be applied to railways, but this is a paradigm shift in railways because traditional railways, I mean, most of the railways that you have nowadays, you need safe separation between trains. So you cannot make trains too close to each other because that would be a safety concern and would not be accepted by railway people who are very conservative. So they don't accept innovations like this. But it is that started with as a visionary paradigm, now is progressively being accepted. And in several research projects, not only this one, it has been addressed, this concept of virtual coupling. And in virtual coupling, you have a moving block enriched with the possibility of virtually connected trains. So you have two or more trains that run as they were single train. And this, of course, the implication is that you have much more rail capacity because you don't have to waste a track to separate part of the track to separate the trains. So you can have higher performance, higher capacity of rail tracks. This paradigm can be really supported by artificial intelligence because you can have adaptive control, intelligent control that helps optimizing the performance of virtual coupling. So not everything is deterministic in virtual coupling. You can imagine that there are a lot of uncertainties, and AI from the control system perspective can make this virtual coupling more intelligent, so improve the performance, improve the safety of the system. So this is one of the several things that were several applications of AI within railways is the supporting this paradigm of virtual coupling.
Okay, the next question is self-driving cars and trucks and even ships have been talked about for many years now. At least I haven't heard about autonomous rails much, whereas it seems to me that because of the presence of the tracks, it should have been the first problem to be addressed. Do you have any thoughts on that?
Well, actually, it very much depends on what you mean with the autonomous trains. Because if you mean driverless trains, and you refer to the grades of automation that I have showed in one of my initial slides. That is something that we already have in many railways nowadays. Most of them are airport shuttle trains or subways, and I can mention several in Europe. I think one of the first has been the Dockland Railway in London, which has been one of the first driverless train in Europe. You have a steward on board, but you don't have any train driver. Everything is automated. But then if you move to Paris, you have line 14, if I'm not mistaken, which is completely driverless, and it's not a new line. It's now it's quite a lot of years that has been active. In Rome, you have line C. In Copenhagen, you have the City Ring, and I mean, in all big European cities, you have driverless trains. But as I said, those are mostly metros, and they have no driver. They don't need any staff on board, but they act as elevators. You know how elevators work. They are autonomous, okay, because you don't need any driver, but they cannot deal with any kind of uncertainties. So in current driverless railways, in these metro railways that I mentioned, you have platform screen doors. But if you have someone on the track, for some reasons, a person can access the track, the train has no possibility to detect this person on the track and to prevent the accident. So this is the difference between driverless trains that, as I said, have been around for decades. It's not a new thing, and autonomous trains where you have AI and machine learning. So you have artificial vision. You can deal with uncertainties. You can adapt to the environment. You can detect obstacles, and you can also learn from the experience. So this is the big paradigm shift from automation to autonomy.
Okay, the next question is about certification, explainable AI and TUV, XAI and TUV certification. So the question is, are there any products in the making which are certified or close to getting certified status?
Well, it also, now again, the answer is it depends, because if you use AI in its most powerful evolution that we have nowadays, which is deep learning, artificial vision with convolutional neural networks, and you use that technology to recognize signals, detect obstacles, to avoid accidents, I would say no. There is no product that is already certified or even close to get certification. With close to get certification, I mean that it will happen in the next few months or in 1 or 2 years. Not to my understanding, and not to according to the feedbacks that we received from railway experts, people from industry, because you know, when you work on academic research, you never know what's happening inside the companies. So we got this anonymous feedback from people working in companies, but they were also very skeptical about the possibility of having the certification of intelligent products or machine learning technologies very soon. But for some other technologies that are not very much based on AI, if you use, for instance, active infrared, ultrasound, or radars, or other technologies, they got some kind of certification to detect vehicles. So you have technologies to detect vehicles in some conditions, but they are not the intelligent technologies. So my feeling is that you need the combination of technologies. You cannot only use artificial vision, but using artificial vision together with some other technologies that are less based on AI could be a good combination of power of deep learning, for instance, and reliability or certifiability or of simpler technologies.
So I was also curious to know the impact of AI Act on your work. Do you see any impact that?
Well, I would say I'm not an expert of the AI Act because it's more materials for for lawyers, for legal people. But for what I know, it is a very important thing that it has been formalized and approved. But it doesn't change very much the situation from a technical perspective because we were aware. I mean, at least the people like me who have worked for many years on safety critical systems, I knew it perfectly that it was not possible to certify AI easily. Because when I started working on safety critical systems, and I worked in the railway industry, one of the things that I remember clearly is that in these SNREC standards for the RAMS standards for reliability, availability, maintainability, and safety that was used for the certification, you had this list of possible techniques to be used, and there was, for instance, formal methods highly recommended. So there was this indication of using formal method to demonstrate the system is safe, and it was highly recommended. But there was a mention of neural networks, and for neural networks there was clearly written not recommended because it was not predictable. So it was something that was not acceptable to use these technologies to control safety critical systems. So for me, it was not a novelty to see that in this AI Act you have this distinction of on the level of criticality of systems, and in case of critical systems you need approval and certification. But for many other people working in other sectors or maybe less critical sectors, there were a lot of there are a lot of maybe not so obvious indications on how they should manage the data of people. So there is emphasis on privacy, on confidentiality, non-discrimination, absence of bias, transparency. So I think that it was probably more important for other sectors rather than this sector of safety critical systems, because I mean everybody working on these sectors knew that it was not possible to use these technologies easily when they are involved in safety critical control functions.
Yeah, thanks for the answer. I don't see any more questions. There are a few thank yous to you, Francisco, and there's one last question about the slides, whether they'll be posted. So the practice has been to post slides on our website, provided the speaker shares them with me. So I don't know if Francisco would like to share the slides.
Yeah, sure, I can share the slides. No problem.
Okay, then I'll post the slides to our website, and the video will be available on YouTube. And I'll also submit it to IEEE TV, so you can watch it later as well. So with that, let me share my screen for a little bit. So if it was, I hope everyone is able to see the certificate.
Thank you very much.
Yeah, so if it was in person, we could have given you a plaque and some memento, but in the absence of it, I just wanted to present this certificate of appreciation for taking your valuable time. I know it is evening for you, so really thanks a lot. Yeah.
It has been a pleasure. So thank you very much for inviting me, and I was really glad to give this talk. So it has been a pleasure.
Yeah, thanks a lot. I'll end with some of the upcoming events. So next month we'll have this second international conference on applied data science, where we are inviting a few distinguished speakers like Francisco. I mean, Francisco's event was last month. Sorry, this month. Next month will be this ICAT's conference. We have speakers from multiple countries, Canada, India, Greece, and so on and so forth. And we'll have a panel discussion on should AI development take a pause. So hopefully it will be very interesting. We have some industry participation also. So please feel free to register. It's again free. This is going in the reverse direction. How do I do this? And then in August, I'll be talking on data warehouse, a traditional data warehouse. So that also will be virtual and it will be a free event. And October is when we have the IEEE day. So that's when we are planning for a panel discussion again on ethical aspects of artificial intelligence. So please watch out for details, and hopefully you will stay in touch with us. So with that, I conclude the session, and once again, thank the speaker, Francisco, Dr. Francisco. It was really nice. It was very insightful, the talk, and it generated quite a lot of interest, as you would have seen from the questions. So thanks a lot again for all your support.
You're welcome, and thank you again for inviting me.
Yeah, sure. Bye, everyone. See you around in our future events.